Right, well, first of all, I would like to thank the organizers for inviting me to speak here. And I should mention that a part of this project is joined with Jared Weinstein from Boston University. So on this slide, I just have some kind of very general themes that underlie this project. So of course, the first two of them are, well, essentially the same, or at least they're very closely related. So one of the distant goals that Jared and I have is to try to find a purely local proof of the local Langlands correspondence, and hopefully to also be explicit. And the way we plan to approach it is to figure out, again, a purely local way to compute the cohomology of the Lubin-Tate tower, so without using Shimura varieties or anything like that. And then the second theme, which turns out to be pretty closely related to the first one, is to give some kind of a geometric construction of supercuspidal representations of reductive p-adic groups. So I'm looking for something that's in the spirit of the Deligne Lusztig theory. Okay, so here is a rough plan of the talk. Right, so first I'll talk, I'll say a few words about the Lubin-Tate tower without going into any details. And I'll mention how it's related to the Deligne Lusztig variety for GLN over a finite field. Then I'll explain a kind of analog of this Deligne Lusztig picture that's, well, it's classically done for reductive groups. But it turns out that there are some situations in which you also have an analog of that picture for certain unipotent groups over finite fields. Then I will explain how that story is related to the local Langlands correspondence and the Jacquet-Langlands correspondence. And then in the second part of my talk, I will discuss, well, an analog of the Deligne Lusztig theory, which exists for certain representations of reductive p-adic groups. Okay, so let's start with a bit of history. So I'm always going to work over a local non-Archimedean field with finite residue field, which I will denote by FQ. Now I should say, so I'm not sure if I will remember to mention this later, but unfortunately, some of the main results that we have right now, they are only valid under the assumption that F has positive characteristic. Okay, so at least for part of the talk, this field F will have to be a formal Laurent series over FQ. Okay, so let's recall briefly how the Lubin-Tate tower is defined. So for simplicity, I'm going to think of it as a tower of rigid analytic spaces over the completion of the maximal unramified extension of F. So in particular, x0, so the zeroth level of the tower, so that's the one which has no level structures, is the moduli space of deformations of some fixed height n formal OF module over FQ bar. So as usual, OF is the ring of integers. And also remember that, so this x0 is really, as a rigid analytic space, it has a very simple structure. It's just an open polydisk of radius 1 of dimension n minus 1. Okay, now if instead of just looking at deformations of this formal module, you start looking at deformations with level structure, then you get a whole tower of rigid analytic spaces, so x0, x1, x2, and so on. And then, so these spaces are easier to analyze in the case where F has a positive characteristic. And in particular, for the first level of the tower, it's very easy to write down an explicit equation for it. And so you can realize it as an analytic subspace of a closed polydisk of dimension n that's cut out by a single polynomial equation in this case. Okay. And then by looking at this explicit formula, it's not hard to find a certain open affinoid subspace of this x1 of the first level of the tower and compute its special fiber. And so the word good reduction just means that the special fiber of this affinoid is smooth. And then one realizes that this the reduction of this open affinoid admits an action of the group GLN of FQ, the finite general linear group. And then the cohomology of that reduction realizes the cuspidal representations of this finite group. And in fact, this is historically how the first example of a Deligne Lusztig variety was actually discovered. Yeah, so if you look at the Deligne Lusztig paper, you see that they attribute like the first example of a Deligne Lusztig variety to Drinfeld. So this is actually how Drinfeld discovered that example.
In the Lubin-Tate tower?
Yeah.
He really was looking
Yes,
at
that's
that,
right.
not
Yeah.
Monty?
Yeah. So he found this example after he wrote his paper about elliptic modules. Yeah. So for the purposes of what I will talk about in the second part of the talk, it's also useful to recall a little bit about the general setup of the Deligne Lusztig theory. So let's take any connected reductive group over an algebraic closure of FQ. Now I'm going to denote by FR sub Q the Frobenius relative to some rational structure over this finite field FQ. Okay, and let's pick a maximal torus in G which is stable under the Frobenius. Okay, so of course over FQ bar we can choose some Borel subgroup containing this maximal torus. We can look at this unipotent radical, which may not be stable under the Frobenius, and of course in most interesting cases it is not stable. If you're wondering about why I'm denoting it by Y rather than U, it's because, so a little bit later I will use the letter Y for kind of a similar purpose, but in that other context Y will not be a subgroup at all, so it's better not to use a letter like U. Okay, and so then we look at the preimage of this unipotent radical Y under the what's called the Lang map. So this map G goes to Frobenius of G times G inverse is the Lang isogeny for the group G, and we look at the preimage of Y under this map. And let's call it X. So this X is not quite the Deligne Lusztig variety, because if you actually look at the original definition of the Deligne Lusztig variety, you see that you need to mod this out by a certain unipotent subgroup acting on this variety by left multiplication. But since that's a connected unipotent subgroup, modding out by it does not actually change the cohomology of the variety, or rather maybe it changes it up to some cohomological shift, which is not very relevant for our purposes. So we might as well work with this X. Okay? And now if you look at the formula defining X, you see that first of all, because this expression is invariant under right multiplication by elements of G of FQ, then you obviously have an action of, well, G of FQ, which is the same as the Frobenius fixed elements in G, this group X on X by right multiplication. And on the other hand, because the torus normalizes Y, it also acts, well, the Frobenius invariant elements of the torus act on X by left multiplication. Okay? And so in particular, given any one-dimensional character of this group of rational points of the torus, you can look at the part of the cohomology of X on which the subgroup acts by the given character. Okay, and because these two actions obviously commute with each other, this subspace of the cohomology is a representation of the group of rational points of G. Okay? So this is kind of the essence of the Deligne Lusztig construction, and it's going to be a common theme for everything that I will talk about today. So we'll see something like this occurring for a certain type of unipotent groups, and that is related to the local Langlands correspondence. And then something similar also happens for reductive groups over p-adic fields. Okay, so now let me talk about this unipotent analog of the Deligne Lusztig theory, which I promised. So it's not going to be something that works for an arbitrary unipotent group, and in fact, I don't think that there is any hope of having kind of a uniform theory like that works for any unipotent group. So for now, I'm going to focus on a very special family of unipotent groups over finite fields. So for any number n, we have an n-dimensional unipotent group, which consists of just think of it as formal expressions like that. And of course, you multiply them using distributivity as always. But now to be able to multiply any two such expressions, I have to tell you how to multiply things by this variable tau on the left. Okay? So the rules are, first of all, you require that tau to the power n plus 1 is equal to 0. And then if you commute tau past any scalar, then you get that scalar to the power q. Okay? So these two rules completely determine the multiplication in this group. And now, as promised, so in this case, we take this subvariety Y to be something that's, well, it's not a subgroup. So it's defined by the vanishing of this last coefficient. Okay? So it's just a hyperplane inside this unipotent group U. Okay? But otherwise, the construction looks exactly the same as before. Right? So the Frobenius is, of course, what you would guess it is. It's just raising all the coordinates to the power q. Then the only slight difference is that instead of considering the Lang isogeny for the Frobenius corresponding to fq, as we did on the previous slide, I'm going to take the Lang isogeny corresponding to the q to the nth power Frobenius. Okay. So now again we take the preimage of this subvariety y under this q to the n power Lang map. That preimage is some smooth hypersurface in U. And again, just for a trivial reason, the group of fq to the n rational points of U acts on this hypersurface X by right multiplications. And now it turns out that the cohomology of this variety also realizes many interesting representations of this group of rational points of U. Okay. So to give a kind of a completely precise statement of the theorem would require too much notation, so I'm going to kind of summarize the important facts without going into too much detail. Right, so first of all, just as a quick observation, so the center of this group U is just the elements where only the last coordinate is allowed to be non-zero. And then similarly, the center of the group of q to the n rational points is just, again, the group of fq to the n rational points of Z. So as a group, it's just isomorphic to the additive group of fq to the n. Okay. And now if you pick any additive character of fq to the n, right, so you can think of it as a character of the center of this finite group. Of course, in general, there may be many different irreducible representations of this group which have this particular central character. Okay. But however, it turns out that there is exactly one of these representations which also occurs in the cohomology of this variety X. Okay. And now another important fact is that the multiplicity with which it occurs is always equal to 1. And like I said, in the actual theorem, we are much more precise than this. So we can say exactly what that representation is, meaning that we can say how to explicitly get it as the induced representation from some subgroup. And then we also know its dimension. We know in which cohomological degree it sits. We know how the Frobenius acts on it, and so on. And then one interesting consequence of this computation, so this consequence has nothing to do with the local Langlands program as far as I know, but it's a somewhat interesting result in its own right. So the fact is that this variety X, so remember X was defined as the preimage of that hyperplane Y under the Lang map. So this variety turns out to be a maximal variety over this finite field fq to the n. Right, so maximal means that if you look at the dimensions of the cohomology groups of X, right, so that's something that you get from the computation of the representations of this group which occur in the cohomology. If you look at the dimensions of the various cohomology groups, and then if you look at Deligne's theorem from his second paper on the wave conjecture, you see that theorem gives you an upper bound for the number of rational points in terms of the dimensions of these cohomology groups. And it turns out that for this particular variety, that upper bound is actually realized. Right, so more concretely, it means that the Frobenius acts on the various cohomology groups of X with eigenvalues. Well, it acts actually by scalars, which have the maximal possible absolute value, and moreover, the signs match up exactly right, so that when you apply the trace formula to compute this number of rational points, all the signs turn into +1, so there are no cancellations, and you get the maximal possible number. Okay. So now let me say a few words about how this variety X is related to the local Langlands correspondence. Okay. So this started with the work of Jared Weinstein from 2009-2010, in which he found a certain intermediate space in the Lubin-Tate tower. So remember that this X1 and X2 are the first and second levels of the tower, and discovering X1, or the covering of X2 over X1 is a Galois tile covering whose Galois group is something like the n by n matrices over FQ. And then what I mean by an intermediate space is that this X1.5 is defined explicitly as a quotient of X2 by a certain subgroup of this Galois group. And then inside this intermediate space, or rather, well, not inside the space itself, but you have to extend the scalars to a certain finite wildly ramified extension of this maximal unramified extension of F. So after you make that base change, you can find a certain open affinoid subspace that has good reduction, whose special fiber turns out to be isomorphic exactly to this variety X that was discussed on the previous slide. And so now what does this actually have to do with the local Langlands correspondence? Right? So let me introduce a little bit more notation. So I'm going to take D to be the central division algebra over F that has invariant 1 over n. And then by WF, I will denote the Weil group of this local field F. And yeah, so there is a certain, so if you look at this triple product of GLN F times the units in this division algebra times the Weil group, so I guess it's not quite this product, but some large subgroup of this product acts on the whole Lubin-Tate tower. And then there is a certain open subgroup J inside this product, which is essentially the stabilizer of this open affinoid Z. Okay, so that's a subgroup whose action on the Lubin-Tate tower preserves this affinoid Z. So by functoriality, this subgroup acts on this variety X, okay, and therefore it acts on the cohomology of X. Okay, moreover, for essentially trivial reasons, the cohomology of X, well, let's take the degree n-1 cohomology in this case. So the cohomology gives you a smooth representation of the subgroup J. Okay, and then you can form the induced representation up to the whole triple product. And the theorem is that when you form this induced representation, it realizes the local Langlands correspondence and the Jacquet-Langlands correspondence for a certain class of supercuspidal representations of GLN. Okay? Now, what do I mean by this? So first of all, of course, since this affinoid Z somehow only accounts for a very small part of the cohomology of the Lubin-Tate tower, we cannot expect it to realize the full Langlands correspondence or even a large part of it. So it accounts for some, for some specific family of representations. And well, explicitly, so here is a characterization of the representations that you see in this correspondence. Right?
Which open subgroup exactly?
Yeah, so that's the harder part. I mean, yes, I can say it, but again, this would require a lot of additional notation. I think really it's best to think of it as just a stabilizer of this open affinoid inside G. But I mean, yes, we can compute it explicitly. So maybe after the talk, or if you're interested, I can write down the explicit formulas for you. But it's not a very pretty description. Okay, so let me just briefly describe the representations that you see in this particular part of the correspondence. So I'm going to call E the unramified extension of F of degree n. Okay. And now let's take any level 2 character of the multiplicative group of E. Right, so level 2 means that it's trivial on 1 plus the square of the maximal ideal and not trivial on 1 plus the maximal ideal. And it's non-degenerate is kind of a technical condition. It means that you cannot decrease the level of this character by twisting by something that comes from a norm to an intermediate extension. All right, so now given any such character, you can easily produce an n-dimensional irreducible representation of the Weil group from this character. And the representations of this type are exactly the ones that you see occurring in this correspondence. So I know maybe it's not completely clear what I mean by, when I say that this representation realizes the local Langlands correspondence. So what it means is that, so this is some smooth representation of this triple product G. And when I say that it realizes a part of the local Langlands correspondence, I mean that if you look at the irreducible G subrepresentations that occur in this induced representation, and you write each of them as a tensor product of something that comes from here, tensor something that comes from here, tensor something that comes from here, then all of those irreducible subrepresentations occur with multiplicity 1. And if you look at how those tensor product decompositions sort of match the representations of this group with representations of this group and of this one, then those correspondences are exactly the same as the Jacquet-Langlands for this pair of groups and the local Langlands for this pair of groups. So this was the first part of the talk. Now in the second one, I want to talk about a p-adic analog of the Deligne Lusztig theory. So actually, this idea goes back to an article by Lusztig in the Corvallis Proceedings. And here is what the story is about. So again, I'm going to take F to be a local non-Archimedean field with residue field FQ. And now I'm going to take a reductive group over capital F and the maximal torus inside this reductive group. So I assume that the torus is also defined over F. And I will make an assumption, which is that there is a Borel subgroup in G, which is defined over the maximal unramified extension of F, which contains this maximal torus. Okay, now of course, I mean, this is a very serious assumption. Right? So for example, if you think of G as being GLN over F, then essentially this means that you can only get maximal tori that come from multiplicative groups of unramified extensions of F. Right? So this is a very serious restriction, and one of the very distant and very serious goals of this project is to try to find an analog of this which works without this restriction that the torus is unramified.
Does it make a difference if you require to be defined over just the unramified closure without the completion?
I don't think so, because, well, I don't think it should, because, I mean, somehow I think the existence of this B can be described by some finite collection of elements of F hat unramified and some finite collection of equations. So I'm guessing there is some kind of approximation result which would tell you that if you can find it over the completion, then you can find it over the field. Yeah, yeah. Okay. All right, so now once we have this Borel subgroup, we play exactly the same game as we did with the Deligne Lusztig theory over finite fields. So I'm going to take this boldface U to be the unipotent radical of B. And now this is just notation, so it's the same as the one that Lusztig uses. So I'm going to denote by these tildes, so G tilde, T tilde, and so on, the groups of points of the corresponding algebraic groups over this F hat unramified. Okay? And so now I'm going to denote by this Frobenius sub Q the automorphism of G tilde induced by the Frobenius, well, by the obvious Frobenius automorphism of F hat unramified. And now once again, so as in the finite Deligne Lusztig theory, we take the preimage of this U tilde under the Lang map. Except that now let's really do what people usually do in Deligne Lusztig theory, which is to mod out by this preimage by this intersection. So the intersection of U tilde with the inverse image of U tilde under the Frobenius map. So if you do the similar thing in the context of the Deligne Lusztig theory over finite fields, you get exactly what's called the Deligne Lusztig varieties in that setting. Okay, so now, all right, so we have this construction. So again, just for kind of stupid formal reasons, the group of rational points of G, which is the same as the Frobenius fixed elements in G tilde, acts on this variety on the right, and then the group of rational points of the torus acts on this variety on the left. Okay, and so once again, modulo the fact that you need to somehow define the homology or cohomology of this X tilde correctly, then given any smooth one-dimensional character of the torus, you can look at the corresponding isotypic component of the homology, and you get an action of the group of F rational points of G on this cohomology. Okay. So let me give a few comments about this. Okay, so this comment is really about what Tom has asked. So the first thing that we need to do is we need to make sense of this quotient as an in scheme over the algebraic closure of FQ. Now, so I think that this is actually possible to do. I mean, there is there is various technical issues that one has to deal with, but it's not beyond our reach. Okay. So now another thing that you need to do is you need to be able to make sense of the p-adic homology. Right, so you might wonder why I'm switching from talking about cohomology in the previous part of the talk to talking about homology in this part of the talk. So this is, essentially the reason is that this variety X tilde is certainly going to be something infinite dimensional. And the reason I'm switching from using cohomology to homology is, well, basically to avoid having to shift cohomological degrees by kind of an infinite amount when I try to define the cohomology of this X tilde. I guess maybe a very simple basic example to keep in mind is if you look at, let's say, an n-dimensional affine space, right, over FQ bar, then if you think about its homology in any reasonable sense, so that's always going to be something that gives you a one-dimensional vector space in degree 0 and gives you zeros in all higher degrees. Whereas if you were to work with cohomology with compact supports, this would give you a one-dimensional space in degree n, and then zeros everywhere else. And then you would run into trouble when you try to take the limit as n goes to infinity. So this homology is essentially just a way to renormalize the compactly supported cohomology groups to avoid this problem. Okay. And so in fact, in his article, Lusztig actually sketched a way to define this homology carefully. And moreover, Lusztig proved something in his original paper, and then he has another article devoted to this topic in 2004, where he proves that in many situations, this isotypic component of the cohomology of X tilde does actually give a smooth, irreducible representation of G. Okay? So what's the problem, right? So it might seem like this is great, and it's the end of the story. But the problem is that there are very few cases where people know what that representation actually is. So certainly it's natural to conjecture that the representation of G of F that you get from Lusztig construction coincides with the one that people typically use in p-adic representation theory, but nobody knows how to prove this. Okay? And actually, I think this is one of the reasons why not many people are even aware of this paper of Lusztig.
I'm sorry, I think you just said this, but I didn't quite catch it. What does it mean to compute a representation?
No, so what I mean is that if you, so let's forget about this whole geometric picture, right? If I give you a connected reductive group over a p-adic field, I give you an unramified maximal torus in it, and I give you a character for satisfying some non-degeneracy condition, you know how to define an irreducible representation of that group, right? I mean, well, you explained part of this in your talk, right? So you take this torus, you fatten it up a little bit, and you take the induced representation. So what I mean by computing this explicitly is to identify these representations with something that can be obtained by that construction. All right, and so it turns out that the problem of computing these representations explicitly turns out to be related to kind of similar to questions that are similar to the ones that I mentioned in the first part of my talk. So in this example, we're going to look at the following situation. So this G tilde, so in other words, if you like, the base change of G to the maximal unramified extension of F is just going to be GLN. Okay? But so the group itself will be not GLN, but it will be the inner form corresponding to the central division algebra of invariant 1 over n over F. Okay, and so the maximal torus, of course, will consist of just diagonal matrices. But now I'm going to take the Frobenius to be not the standard one, which would be just this, but this kind of twisted Frobenius. Right? So first you apply the usual Frobenius to all entries of a given matrix, but then you conjugate by this element of GLN. Okay? And of course, the result of this is that the group of Frobenius invariant points in G tilde is now the multiplicative group of this D. So again, D is the central division algebra with invariant 1 over F. And then E is the unramified extension of f of degree n. Okay, and then the group of rational points of T tilde it can be naturally identified with the multiplicative group of E. Okay, and then for this unipotent subgroup, for U tilde, again, we take the most obvious choice, which is the unipotent upper triangular matrices in G tilde. Okay. And so now we try to apply this construction of Lusztig, and we see what the result is. Okay. So first of all, so what is X tilde in this case? Right. So as I said earlier, in concrete examples like this one, it's pretty easy to give kind of an ad hoc description of X tilde, which avoids questions like, what does that quotient mean, and so on. So in this case, it turns out that X tilde is a disjoint union of Z many copies of some scheme over FQ bar. So I'm going to label them by X tilde with the superscript n. And now if you look at how the group of rational points of G acts on this X tilde, right? So remember that the group is really just D cross, so the multiplicative group of D. Now the uniformizer in D cross permutes, it kind of shifts this superscript by 1, essentially. And then each of these schemes is stable under the multiplicative group of the units of D. And moreover, each of these schemes X tilde superscript n is again pretty naturally realized as an inverse limit of some, basically ordinary algebraic varieties X tilde upper n subscript h. Now the very interesting incidence is that if you look at the part of this X tilde corresponding to, well, I don't know if, the h doesn't really stand for height. It stands more like for something like depth, maybe. So anyway, if you look at the part of this X tilde corresponding to depth 2, or level 2 if you like, it turns out to be very closely related to the variety X that I discussed in the first part of my talk. And so remember, X was the preimage of a certain hyperplane in that n-dimensional unipotent group under the Q to the nth Lang map. So as a consequence, using the results from the first part of the talk, one can calculate the cohomology of this piece of Lusztig's variety. And then using this, we can show that this construction of Lusztig that I just explained actually gives the correct answer for characters of level 2 of this multiplicative group of E. So again, correct answer means that the answer is the same as the one that you would obtain by using the construction that Lauren mentioned in his talks. Okay, then so more recently I've been doing some computations for higher depth. So I've been doing some computations for higher depth, and I guess so what is known at this point is that if you take n equal to 2, so if you look at the multiplicative group of a quaternion algebra, then this construction also gives the correct answer for characters of level 3 and 4, or something like this. But the remaining cases are still very much work in progress. Well, I guess that's all I wanted to say for today.